So today I'm discussing two subjects, but I need to erase the Okay, maybe I need something to erase during the. Okay. Okay, one here, one. So I guess we'll like. Right, this is the two subjects I want to discuss today. And so let's start from with the first. For the second one, I will need also the so you remember that the large deviation function for having a joint fluctuation of rho and j is given by this 1/4 I of which is some I of rho and j, which is given by 1/4 of the integral in dt, the integral in dx of j minus j rho chi to the minus 1 of rho, and j minus j of rho. Okay, where rho and j must be connected by the continuity equation. Now, what I'm looking for is some large deviation estimate for the which gives me the probability for the average current fluctuation, and I think this is one of the most interesting parts which comes out from the macroscopic fluctuation theory. So let me introduce some time average current, which is just the over an interval t, which is just the integral dt over the of x and t. So this is the quantity which I want to consider, and we want to find for very large time the probability of having some value of j, and we expect it to be of the form t, and then some large deviation functional phi of j. Now, this is in fact what you can prove in models, and some remarks. This J, which is defined here, must be something which is divergence-free, because if it is if it has a non-zero divergence, what happens is that your system either gets empty or you have it gets full and nothing happens. So, in fact, you can prove that if this is not divergenceless, then this probability is zero. So now this functional phi, I will define it in terms of this quantity here, and this is this phi of j will be defined as the limit for t going to infinity of 1 over t of this I of the inf where the infinite is taken over a certain set A of t, and the A of t is defined in the following way. It's the rho and j such that okay, 1 over t, this integral it's equal to j, and of course the you have some initial condition rho 0, and then you have that dt of the rho plus divergence of j, it's equal to 0. So this is the definition of my functional, and it's for this type of functional that I can prove, in fact, an estimate of this type. This is more complicated than proving the large deviation estimate in the stationary case and calculate the the quasi-potential V of rho. Okay, so now this functional is a genuine thermodynamic functional. It's a you know, when you have to deal with currents, it's natural to do some kind of space-time thermodynamics, because so here you see we have also the limit of in this definition, and now this functional has some very important properties which qualify it as a genuine thermodynamic functional, and in fact it is convex. So if you have a current J, which is of a J1 plus 1 minus P J2, then you have that phi of J is less or equal than P phi of J1 plus 1 minus P phi of J2. Okay, so it behaves, these are not very difficult to prove, this. And on this, you will find in this review that I will give you the precise reference in the end. Okay, now what I want to discuss, you may, since this is a thermodynamic functional, you may expect that if you get singularities of this quantity, then they would be associated to phase transitions. Okay. Now I want to discuss under what conditions this may happen, and then For this, I have to discuss first a simplified situation, which was discussed for the first time by Bodinot and Derrida, and they called it the I don't remember the name they gave it. They gave it to it. Yes, it's additivity principle. Okay. So what they did, they introduced a simpler quantity, which was simply the so it's something which is independent of time, and actually here they argued directly that, so they suppose that this you consider something which doesn't depend, these quantities do not depend on time, and this then you can identify directly with the time average. So it will be this pair. So it's our I functional, but without the time integration. So it's J minus J of rho, okay, minus 1 of rho, and J minus J of rho, okay? Now you see everything is independent of time, so the constraint of satisfying the continuity equation is automatically satisfied. Okay. Then they considered the maybe let me introduce some. First, I call it this way. Then they introduce, and I call following them U of J. It's not necessary since this depends only on one variable. So this is the inf or rho of U of rho and J.
So here the constitutive equations are not satisfied for U rho J?
No, it's I mean everything is independent of time, so it's automatically satisfied. Okay, then you see, you understand immediately that our phi of J is in general satisfies this inequality, because here you are taking the infimum over a much larger set of currents. Now, when the situation happens that this is strictly less than U of J, then we speak of a dynamical phase transition. And then I will try to illustrate what it is. Okay. So when then we speak of dynamical now the question is whether these transitions actually exist. Now they considered the case. They didn't think of this possibility, and in fact, in general, these functions are defined in this way. In general, is not convex. So it is convex in certain situations. For example, if you have the simple exclusion process without external field, then this then in this case, in fact, you can prove that this function here you have an inequality in these situations. The same is true for the zero range process or for the KMP process. Now, this is our usual group. With our usual group, we introduced this, which was the natural thing to do in the macroscopic fluctuation theory. And then, of course, we asked under what conditions here you have equality.
These are independent of time. Why? Why you take this? Are you in the stationary state or what?
No. I mean, so the idea, I think, of Boudinot and Derrida was that suppose you consider some average current, then this, I mean, here you, when you do this calculation of this minimization, then for them it was a natural assumption that the rho that you would get optimizing this quantity would be time independent.
You take an average current up to some time horizon.
Well, then I mean, you think it's over an infinite. Suppose, I mean, suppose you, okay, consider this usual functional. Then you are considering essentially fluctuations which are time, which coincide with their time average.
And you send the time average to infinity.
Yes, yes.
And then there is a rho that corresponds to that, which is...
Yes, which is usually the terminology is the rho supporting the current fluctuations. Okay. Now, so the natural question, since we had introduced this phi of j functional, which is always convex. That is the big difference with the other one. So you want to know under what conditions you have equality. So phi of j is equal to u of j. And then you can give, in fact, some sufficient conditions for this to happen. And the sufficient conditions are the following.
Sorry, why do you say, I mean, why is it, what is happening physically if phi j is strictly less than uj? You say there's a dynamic resistance.
Then, if this happens, I say that there is a dynamical phase transition has taken place.
What does that mean? I mean, physically?
I will illustrate it. Okay. So the question I am asking is under what conditions I have this situation here. And the condition is the following. Oh, I've already lost my... The condition is the following. So we have the our transport coefficient d and chi, and the condition is that, so let's say the product is must be less or equal than d prime of rho, and yes, k prime of rho. Now you see this is this condition we proved, well, you have to use some convexity argument and so on and so forth. So it's a technical. But so this condition, then you can see immediately that it is, for example, if you take, this we proved in absence of external field. So it was only boundary driven situation. And then, and in also, well, no, this is in general, but then we consider in particular the geometry in which you have periodic boundary conditions. Now, so take, for example, the simple exclusion. This is constant, so the right-hand side is 0, and the second derivative is negative, so it is satisfied. But on the other hand, it's not satisfied, for example, for, so for the, so for symmetric simple exclusion, then it's okay. Then for the Kipnis-Macchioro-Pessutti model, in which, so here the chi is equal to rho 1 minus rho. On the other hand, in this case, this doesn't work, and because the chi is equal to rho square. Chi is equal to rho square in this case. So okay, d is again equal to 1, and so the second derivative is positive. Okay. Then we try to see whether we could find a rho which is time dependent, supporting the fluctuations, which realizes the condition of having phi of j strictly less than. And then I will write what it is, this. But so think of this condition, all this applies also to an equilibrium state. So takes the, for example, the KMP model and on a ring. Then if you consider small fluctuations, then nothing happens. If current fluctuation is supported by a rigid motion of the whole system. However, if you take very large current fluctuations, then a traveling wave starts. And then so you have something. So this is interesting also because it spontaneously violates time translational invariance. So in fact is this is what I call a dynamical phase transition. That is, we studied mainly this case, and then, for example, instead for the simple exclusion process, in order to have a phase transition, because here it is always satisfied, but then if you put an external field, the situation changes. And that is what was studied, for example, by Bodinot and Derrida. And they made well, the study was not entirely conclusive because they used perturbation theory, but they in fact showed that, and showed also numerically, that in fact in the simple exclusion, with a sufficiently strong external field, you have such a transition, and you get, in fact, a traveling wave.
So just to clarify, external field is the same as asymmetric exclusion, or not?
External field is weakly asymmetric.
Oh, weakly.
Weakly asymmetric, yes. Okay, While in the case of the KMP model, the argument could be more general, and in fact, you can prove the following. You suppose you introduce a row of T and X of the following form. You take some rho 0 of x minus vt, where v is a parameter, is a velocity here, and then you consider a j of t and x of the form, the time average, plus a perturbation of the form v times rho 0 x minus vt minus rho. And then you can verify that all the conditions, continuity equations, everything is satisfied with this choice. And then you can show that, in fact, in this situation, thank you. In this situation, you have that phi of j is less than, you gain, I mean, that is less than v over 4 times the integral in dt v minus 1 of u of rho t and j of t. So that you could do by argument, by convexity arguments, and rather the argument is very general. Then there was a beautiful simulation done by Hurtado and Garrido, where they really showed that for small fluctuations, you get a flat rho, and then for when you go to y, you see the rising of the peak of the traveling wave. So this is let's say that for the KMP process, the fact that you have this transition is proved rigorously, but for the simple exclusion, when you have a sufficiently large field, maybe it's practically proven, because and I mean, concretely, it was seen in perturbation theory. Now, I want to speak very recently Ackermann's and Spielberg, I think is a student of him, proved what I consider a very important result, that this condition that we had proved to be only sufficient, it's actually necessary. So they actually, I mean, here we formulated this condition for every row, arbitrary row. Well, what they what they start, so suppose you call rho star the optimizing row in the Bodino-Derrida functional. Then they start this relationship in the case when you calculate it on this supporting, and then this is d prime over rho star and p prime over And then they studied the stability of this object, of the supporting row under time-dependent transformations. And they found that in linear stability, then they found that actually this condition is violated. So okay, if you don't want to have the phase transition, this must be satisfied. So they call it Le Chatelet principle, and in fact, it's now it becomes a very strong condition. And this is a paper which appeared 2 or 3 weeks ago, and I think it's a very good result.
It's a rigorous proof.
Well, I mean, it's a physicist-style paper, but is obtained with the explicit calculation. I mean, they study the linear stability, so that they can do explicitly. It's at the same level of the Bodino-Derrida study for the... Well, I mean, explicit calculations are usually serious things. I mean, even if... Okay, so I think that then there are other other results. There was a paper by this current fluctuation. So I mean, now it's established that this fluctuation, the phase transitions exist. I mean, and they exist in models that we control also sufficiently well mathematically. Now there was another property which was proved a couple of years ago by Ackermann, Spielberg, Derrida, and Bodino of universality properties of these current fluctuations. And this they studied the case. So the problem is the following. Suppose we consider current fluctuations in dimensions higher than none. So you consider current fluctuations in d dimensions. So, for example, you consider a situation that is your your system, the size of your system. And suppose that you have, for example, a region here and a region here, let's call it A and B, in which you have sources of currents. So you have differences in chemical potentials, so the current is flow. But the current is flowing everywhere. I mean, in particular under. Now, the interesting property is that if you calculate the cumulants of the distributions of the fluctuations and you take the ratios, you get exactly the same results as in one dimension. Everything, I mean, the pattern can be much more complicated, but in the end, everything goes as if you had just a one-dimensional system between. And actually, the mathematical result can be formulated in this way. I am not sure it's formulated in this way in the paper, but it's formulated in this way in our review. So call phi star of S the Legendre transform of phi of j. Okay, then you have you can formulate their result in the following way. Okay, so I call phi star of S, it's equal to the capacity of AB phi 1 star of phi 1 star of S. Okay, so this is the Legendre transform of this functional. So it is actually the generator of the cumulants of the fluctuations. And then what is this capacity? Well, you consider a condenser, an electric condenser, done by your by lambda A and B, which is a purely geometrical quantity, because we know it depends on the geometrical. And this is the coefficient which connects phi star of S to the one-dimensional case. And I think it's a very beautiful result. And this is done quite generally with the macroscopic fluctuation theory. I mean, you have to. Okay, so I think that this is more or less what I wanted to say about current fluctuations. So let's now go to a different subject, and I have 52 minutes. Okay. Now I'm using these slides because, I mean, there are some long equations which are long to write, and it's okay. So this is the slides I prepared for this. Okay, this was the abstract. So suppose you consider a transformation in which you go from one state to another side. So you go from a density profile rho to a density profile rho t in some time t. Okay. Equilibrium, non-equilibrium, station. I mean, here are arbitrary profiles. So and then you want to study the no, there was one thing I wanted to add to the previous case. This functional phi of j satisfies the Galavotti-Cohen symmetry, and the fact it's equal to, if you want, the integral dx of j external field, plus you have a term where you have the integral on the surface of your system of d sigma, and then you have the chemical potential, and then you have the external normal, and then you have the J. So this is the Galavotti-Cohen symmetry, because you see this is the odd part of this functional, and you see that it is universal in the sense that it doesn't depend on the particular model. What you have here is all the power dissipated during the process, during the fluctuations. So that was the last remark I wanted to. Now, so let's make the energy balance in a transformation. So So the work here we have only one. In general, you may distinguish between work and heat, but here I mean, this is all the energy which is exchanged between. This part here is the energy associated to the work of the external field, and this is with the exchange with the reservoirs that you have. So, I mean, this is exactly what I said. Now, you can do some transformations of this equation in the sense that, you see, no. Okay. You see, this surface term, you can transform using the divergence theorem. And because you can extend, you know, you remember the chemical potential is connected with the equilibrium free energy, and the equilibrium free energy is defined everywhere. So you can extend your chemical potential inside the system. And then, but then you use in an essential way the Einstein relationship, and then you arrive at this formula here. So this is the variation of the equilibrium free energy calculated on the initial profile and the final profile. So these are not the general equilibrium profiles. And then you see this is a dissipation term. It's a positive term, quadratic, which includes everything, both the interaction with the reservoirs and the external field. And F is the density of the equilibrium free energy. You see, this is it's a physical relationship because you have used the Einstein relationship. It's not simply an integration by part. And then you see, since this is positive, you find that this W is larger than this variation here, which is which is essentially the Clausius inequality. And so it's the second law of thermodynamics obtained dynamically. So here is the calculation, and but I mean the essential point is the use of the Einstein relation. And then, so our basic equation is the following: that this is this expression here, which is the energy balance, is given by these two terms, and this is the total current. Okay, now something which you have to. That is an important remark that I think was made even in some vague way by Ono and Paniconi in 1998. That you see, when you deal with the transformation between non-equilibrium states, stationary states, for example, so yeah, you may consider a transformation which is also in the end infinitely slow between a stationary state and another one. Just to keep the system out of equilibrium, you have to spend an infinite quantity of energy, because I mean, this is energy consuming to keep the system out of equilibrium. So so in order that a relationship like the energy balance I wrote keeps its meaning for an infinite time, relaxation is exponential. This part will remain finite for any t, and in fact for an infinitely slow transformation will go to 0. And well, that is what I remarked yesterday, that if you are in a stationary state, so this part is missing, then the whole current is given is just the GA. Okay. So. Okay, then we define this renormalized work, which is the difference between the equilibrium free energy plus this part, this dissipation related to the symmetric part of the current. And again, this is positive. So you have a kind of non-equilibrium clausus inequality, because if you throw away this, you have this thing. And you can also show that in quasi-static transformations, so that you can understand, because if you consider a very slow transformation, the system is at any time in an almost stationary state. So this current will be very small, and this is quadratic. So will be small squared, but then you have an infinite part which comes from this integration, but still you get something which remains small. So in the static limit, you get equality in this relationship. Of course, if you are in equilibrium states, the GA part is missing. So if you consider equilibrium states, the renormalized work coincides with the whole work. There is no other part. Okay. Now, this you can see you have a nice interpretation of the large deviation functional for the equilibrium, for the stationary situation, the V functional that I introduced yesterday. So suppose you consider the following transformation. You are in a stationary state. You change instantaneously the boundary conditions, and then the system will not be anymore in a stationary state and will relax to a new stationary state in agreement with the new boundary conditions. And then, I mean, you do a simple calculation, and then you realize that the quasi-potential in the final stationary state, but calculated in the initial state, in fact, is what is usually called the excess work. And I mean, this is yesterday I said that engineers call it availability, because I mean, it's also coincides with the maximal work that you can get from a transformation of this kind. And the only thermodynamic text where this availability is mentioned is Pippard. Introduction to Thermodynamics. It's a very old text of the 50s, so it's 60 years old. And okay, of course, there is not only one way to renormalize, and there was another way of doing it, which was introduced by Christian Maes and Nietochny. It's more complicated because what they do is that they compare the system with a different system in which you add an external potential in such a way that the stationary state is also a state of minimal entropy dissipation. And then well, here I have put we can do the comparison, because what they do is done only for systems of a finite number of degrees of freedom. So it's difficult to compare in general. But if we take the ideal gas, so independent particles, we can compare their calculation, their what they do with us. Well, here I don't describe in detail, but in fact, I mean, that is what they do. They introduce an additional potential, this U, in such a way that you get a stationary state, which is, in general, I mean, a stationary state is not, it doesn't correspond to a minimum of entropy dissipation. But you can arrange things in such a way that the things coincide. So, I mean, anyway, the Clausius inequality that they get is the same as, in this case, is the one also we get. So, it's nice to have a Clausius inequality for non-equilibrium. The point is that you see the crucial role that this quasi-potential plays, because to make the splitting, you have, except in simple cases, you have to calculate first this, or you can measure it, but you cannot measure it by measuring fluctuations, because this would take the age of the universe. But you can, for example, you can expand your V, the quasi-potential around the stationary state, and then you measure the, this is the generator, I mean, it's connected with the generator of correlation function. You can measure correlation functions, so you can approximately measure this V. But I mean, it's really a crucial quantity in non-equilibrium, because it's at the origin of this splitting. So you can calculate with solving the variational principle by numerically. But anyway, but conceptually is very important. Now, that's that was the preliminary part. Now I want to develop what we call the finite time thermodynamics. So let me consider transformations which are very slow, but any real transformation lasts only a finite time. Very long, it may be very long, and you have to qualify what it means very long with respect to the system. And so if capital T is the duration of this transformation, the idea was to make an expansion of everything in powers of 1 over T. And so that you do in the usual way, also what Stefano did yesterday. You rescale your time variable, and so you introduce external fields and boundary conditions, which are now time dependent. And suppose this is a protocol defined in the interval 0, 1. Then well, here I call what I call capital T, I call tau, but I mean. So, and you do this rescaling, and then so you get now the following. For the rescaled variable, you can rewrite the hydrodynamic equations and boundary conditions in terms of this scaled quantity, and J of rho is the usual, which, however, now has an explicit time dependence, because besides the boundary conditions, but the field appears, the external field appears in J, so it has. Okay, then you rescale our previous identity in terms of these rescaled quantities, and then you expand. You expand this quantity, and so let us call the first correction 1 over tau, and then higher order term for the density. You have a similar expansion for the current. So the 0 order term for the current is the stationary the stationary current corresponding to rho bar, where rho bar is the stationary profile as if the time were frozen. Okay? And then let me introduce also this quantity, the inverse of the two-point correlation function, which is in fact just the second derivative of the quasi-potential. Okay? And then, I mean, this first order correction to hydrodynamics, so this R of S is, satisfies this equation, which is an inhomogeneous equation where the inhomogeneous part is provided by this stationary state, which however depends on time in this case. So now first you see that the infinite terms when the t goes to infinity cancels exactly from the two sides of the identity. Then you go to the terms of order 0, and this you get a relationship that I've never seen before. You can express dynamically the variation of the equilibrium free energy in terms of the first correction to hydrodynamics. So you see, for example, that if you go, for example, suppose you start from equilibrium states and you go on through equilibrium states, then, for example, this term is missing because here there is the stationary current corresponding to it. But otherwise, if you go through arbitrary states, and this, I mean, this combination can be, you can have all possible signs. So you can begin to ask. So let's take the renormalized work to order 1 over tau, and so the first correction to delta f is given by this object, which is positive, and it has an explicit expression in terms of in terms of the mobility and the quasi-potential, which contains the second derivative. And you can see that in fact it's strictly higher than 0. And so since this represents this dissipation, so it's, if you want, it's a quantitative form of the Clausius inequality. So here you want to, since this depends on the protocol that you have chosen, so you want to optimize it. Okay, and so you want to spend the minimum of energy for this transformation if possible.
What's the difference between this quantity and the quantity for the total work, the unrenormalized work? You also had a correction in the previous slide, which was an integral of the same form.
No.
What's the... No, the previous... Forward. I mean,
which one? This one?
No, you had the same CS. Yeah, okay. This slide.
Yes.
There's no integral here.
No.
Okay.
Okay. So, so you see, if you, for example, you may ask a question of this type. You start from an equilibrium state, and you go to another equilibrium state. Then you ask the question, what is more convenient, to go through non-equilibrium states or equilibrium states? And then you can see what happens with by optimizing with respect to this. And then here we found a very surprising result that now I will discuss. Okay, so let's consider a system in one space dimension in a certain domain, -1, 1. Diffusion coefficient is the general case. Now, this this dissipation, excess dissipation, so it depends on the protocol. So, I remind you that the R, the correction to hydrodynamics that appears is a solution of an equation, the first order modification of hydrodynamics. Okay. So we want to minimize this with these constraints. So you have final values for the initial and final value for these protocols. And you consider, for example, the transformation between an equilibrium state corresponding to the first values and an equilibrium state corresponding to the other. You may, I mean, it's reasonable to expect that it's more convenient to go through equilibrium states because clearly. So, the procedure to answer this question, you consider this system of partial differential equations. These are the Euler equations associated with this minimization problem. And then you introduce an external field like this one. And then okay, this defines a transformation between equilibrium states and true equilibrium states. And then the minimal value of this B that you can calculate introducing the solutions of the Euler equations is given by this expression. Okay? Observe that this depends only on the mobility. It doesn't depend on the diffusion coefficient because we are on a time scale in which at each instant you have rescaled the time, so the system has already relaxed. So if it has a finite relaxation time, then the argument is completely general. It doesn't depend on the diffusion coefficient, the optimal. Okay. Now, to answer our questions, it is convenient to make a change of variables in the sense that, you see, given a state, every values of the external parameters determine a stationary state. Okay, so and the correspondence is you can prove that it is one-to-one. So you can go instead of using as optimization parameters the external parameter, you use the corresponding stationary state and stationary current. Okay. Of course, in one dimension, the stationary current is always axial. It doesn't depend on the. Okay. Then in the new variables, the quasi-potential becomes a functional on the set of density profiles, depending parametrically. Now, your parameters are stationary states and stationary currents. Well, this, maybe I put the wrong. So the quasi-potential solves the Hamilton-Jacobi equation. And in the present variables, the Hamilton-Jacobi equation can be written in the following way. I mean, they're not simple calculations. They are all contained in a paper that appeared after the review, and I will give you in the end the reference. It just appeared in the Journal of Statistical Mechanics, but the calculations are not simple. Okay, then you go on and you calculate in the present variables the functional. And well, here are all the details of the, so I mean, if you want, I can send you these slides, but there is a paper which is much more detailed. Now, if the initial and final state are in equilibrium, an optical protocol consists in a family of equilibrium states, and this you can show by proving that the excess functional in such a situation satisfies in this situation it is a critical point of this functional. Okay. I don't discuss the detail. Now, of course, you can play the usual game. You consider this B as a kind of Lagrangian, and then there is an Hamiltonian structure associated to it. So you introduce, and that is convenient for writing, for using, for introducing this, which are the conjugate momenta. And so what you have to solve is an equation of this type to get the optimal situation. So here is the definition of what you call Lagrangian, but of course, and this is the Hamiltonian, and okay. Oh, this is, I don't know why it has remained this. Okay. So now we consider first the case. We consider the case in which you assume that your transformation goes through homogeneous equilibrium. So you start from a homogeneous equilibrium and you go through intermediate steps which are also homogeneous equilibria. And then you have to solve this equation, and this can be solved easily. And then you have that the B for this solution is given by this expression. And finally, you find that the minimizer of the minimum, the B optimal corresponding to the solution of this equation is given by this quantity here. This is the time derivative, which is of the protocol, which now is parameterized by the stationary state, and it depends on the square root of the mobility. So this quantity has to be constant because it depends only on the initial and final state. Okay, so that is the what you get, and so this is the value of the B optimal. Now, this case we discovered afterwards that had been treated in a well, let me go on first. No, maybe I can mention it now. We discovered that there existed a paper by Sivak and Crookes in the context of finite dimensional Markov processes, when in fact he had found exactly the same solution. But what now I will show, that since now we have infinitely many degrees of freedom, so we have a space structure, we can do much better. So now, so we, I mean, this equation is the Euler equations are trivial if the chi is constant, but otherwise they are not. So in the case of the Gisborne-Landau model, they are trivial. So you have to solve these equations here. Just believe me. And then you can construct by separation of variables the optimal rho bar and pi bar. Okay, and then you calculate the minimal value of the excess functional. And then you see that, yeah, in the previous case, it was 1/3 of rho bar 1. So you get a flat reduction of 75%. But now we have, you see, the optimal solution, and now I will give an interpretation of this optimal solution, depends on space. So it's not, so you go through equilibrium states, but are inhomogeneous non-equilibrium state, equilibrium states, okay? And so the interpretation is the following. You have your vessel, and you have to introduce all the matter to go from one state to the other from the sides. And then they fill slowly they fill the whole vessel until in a symmetric way. This is what happens. Now, this may be difficult to realize experimentally. So, I mean, here you see the gain is substantial. You get a 75% gain in the energy dissipated. Okay. So, I mean, this is, I mean, it's very sketchy what I said. So the only thing is to look into the paper.
To clarify, you still assume quasi-static?
Yes, quasi-static transformations. Yes.
But they still go through equilibrium, not homogeneous.
They go through equilibrium and not homogeneous. Which are the examples of non-homogeneous equilibria? For example, well, the atmosphere and the gravity field is an example. In biology, they use, to separate things, they use high-speed centrifuges. And in those cases, you have a stationary state which is inhomogeneous. Which is, by all means, you may consider an equilibrium state. I mean.
So is the point that if I change my boundary or my fields so that my non-equilibrium steady state changes from rho naught to rho 1,
yeah,
then it will go through this non-homogeneous automatically?
Yes. Not automatically. You have to drive you have to choose the protocol in such a way. Remember that these rho bars are determined by the external parameter. Right. So you have to choose this external parameter in such a way. So the point is that if you go through homogeneous equilibrium state, you don't have to introduce external fields. To create an inhomogeneous situation, you have to introduce an external field. And this calculation determines what is the external field that you have to introduce.
Okay. But it's not as if the system will automatically pick the, I mean, you have to fix whatever protocol.
Yeah. I mean, so you have to realize experimentally your, well, the boundary conditions are always equal. Mm-hmm. But because the equilibrium states, but the external field you have to choose in an appropriate way. So I think physically it's clear, but maybe it's not so easy to create such a field, and you have also to compute how much energy you spend to create such a field. So this is, but you see, in this formulation of time-dependent thermodynamics, you may ask many questions about optimizing things. So it's very flexible in this aspect. So I have a few more minutes. Oh, for Ginzburg-Landau, the calculation is trivial. So for Ginzburg-Landau, in fact, the optimal protocol is a sequence of homogeneous states because the chi is trivial. Oh, you may also discuss optimization in terms of the derivative of our energy balance. And so they're directly in terms of entropy production. And for example, if you take the case of an ideal gas, so independent particle, you can optimize that, and you find that it is consistent with the famous Prigogine principle, which is valid only very near equilibrium. In this case that you have minimal entropy production in a stationary state. And this is the answer of the optimization. And in fact, you see that the first correction is of second order. So Prigogine principle is saved. Now, I want to give another interpretation of the quasi-potential, which can be, you see, it can be discussed in the case, for example, you have initial state and a final state, and it can be related to the relative entropy between these two states. Relative entropy in the sense of Shannon entropy. And the proofs are not entirely trivial, but actually they are not trivial, because you must have a strong form of the local equilibrium. But let's say heuristically is very simple. So this is the definition of relative entropy between two measures. And so the claim is that the relative entropy between the initial and final state is the quasi-potential calculated at the final state, but for the initial value. Okay. So it is like as if the initial value was considered fluctuations with respect to the final state.
Just like the availability.
Yes, but here it's a different point because I related to. So I mean the argument is very simple because let's think of a particle system like a simple exclusion or whatever you want. Then this relative entropy is given by, this is the measure of the system, but then you approximate the measure with E minus the quasi-potential. Then everything becomes almost trivial. You use the law of large numbers, and then you get your conclusion. So it's a trivial calculation. But at first we were a little disturbed by the following fact, that we thought that we had found counterexamples to this conclusion. Because, for example, you consider the Ising model in which at zero magnetic field, and then you have the and then you introduce a magnetic field, and magnetization satisfies a large deviation functional. So, and if you go to I'm sorry. Here, what I change is the temperature. Okay, so I consider an Ising spin, an Ising system at two different temperature, beta 1, beta 0, and without external field. So the average value of the magnetization is 0 in both cases. On the other hand, if you can calculate explicitly this expression, and you find that it is positive. So it seems to be a contradiction. But the point is that that relationship that I have considered applies always to conjugate variables. So if you, instead of considering the magnetization, which is the conjugate to an external field, you consider the energy large fluctuations, then everything comes back okay. So it has always been, it has to be applied to pairs of conjugate. So here we have varied the temperature, so the quantity, the dual quantity is the energy. Okay, so I give only two references, I mean, because in this review we have made considerable effort. You see, this many people have contributed to this macroscopic fluctuation theory, and we have made an effort to, there is a long list of, we have made an effort to include the relevant reference. And this, and the other one is just the paper that I have discussed in these optimization problems, which, I mean, it appeared a few weeks ago. So. And so another, among the things I've mentioned today, I mean, to see also the effectiveness of the macroscopic fluctuation point of view, to read, for example, because you reach this universality conclusion, to read the 2 years ago paper by Ackermans, Derrida and Godinot, and also the recent paper by Ackermans and Spielberg. Well, I think I will stop here. I mean, you must have had enough of all this.
More questions?
So you mentioned that the non-equilibrium steady state is in general not the minimizer of the entropy production functional. I mean, is there something like a variational principle that characterizes the non-equilibrium steady state in general?
No, I don't think you have to go through. I mean, that was discussed in a paper which is hard to find by Ing, Lebowitz, and Spohn many years ago, in some proceedings of some Russian, joint Russian, is that, yeah. You should put it on the archives, that paper. You remember having written such a paper? In which you showed that the question was about the validity of Prigozhin principle. No, you proved that it is true only at first order.
Yeah, that's what I want to say. Yeah, no, that's absolutely correct. I mean, showed, I mean, in a particular case,
that was the question. Order, yes. So, but since this paper is not easy to find, you better put it on the archives. And they showed that already in the next order is not anymore true. I mean,
Any more questions? Okay, thank you. We'll reconvene at 11:50. There's a break right now.